If you are asked what is a random variable, you say x or better real valued measurable function defined on the sample space is a random variable. We need this. I will show you why we need measurable function. Okay, so example of random variable. Suppose we take this. Tossing a coin 2 times. So it is either 2 times head or head, next is tail, or first one is tail, then head, or both times tail. We can define a random variable x as x is number of heads. To be a random variable, what we need? It should be a function from omega to r. This is a function from omega to r because we can define for hh is 2. It is 1. It is 1. So values of x are all real. All these values are real number. Next is what? We have to see x is measurable function. Now remember, singleton set are all measurable. All the singleton set are measurable sets. All the countable sets are measurable sets. So we take singleton 0. Singleton 0 will be in B. We have already discussed everything in terms of measure. Nothing new, same thing. We have already discussed singleton sets are always measurable sets. So this 0 is in B. What is x inverse 0? X inverse 0 is TET. X inverse 1 is HT and TH. X inverse 2 is HH. And in this probability space omega f t, we take f as power set of omega. Power set of omega means all the subsets of omega. These are subsets of omega. Understand or not? We have a probability space omega f p. First one is a sample space, second one is a sigma algebra, third one is a probability measure. The extra condition is probability of omega is 1. Otherwise everything is same as measure space. We already discussed everything here. So we tossed a coin twice. The sample space will be this. We took f as power set of omega, the biggest sigma algebra. Power set of omega means it already contains all the subsets. It contains all the subsets. Now we are trying to define a random variable. We define x as number of heads. Then x of HH, x of HT, everything we can find out. All these values are real number. Next is whether x is measurable or not. So we see x inverse 0 is this, x inverse 1 is this, x inverse 2 is this. And this P, T, H, T, all this belonging to power set of omega, right? This is subset of omega, so it is inside power set of omega. So x is a random variable. Similarly, we can define y as number of tens, and it will be a random variable. So for random variable, we doesn't need p. We never use p. We check. We define x as number of heads. We just need x of h is this. We just check whether x inverse 0 inside this or not. So just this one and this one is sufficient to define random variable. We don't need any probability, right? We don't need any probability. Just a set and a sigma algebra. Then we can define random variable. Okay, next it's better we take the sample space as 3 times tossing a coin 3 times. What will be the sample points? Sample points? And how many? Missing. Sometimes. H. And can we get another term? Any other term? There should be 9 terms. H, 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 T, H, H, T, H, H, T, H, H. So T, H, T is there, okay. T, T, H is there, H, T, 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 T. It should be another term. Oh no. Okay. Hey, how to calculate? How many terms? 2 power of 3. For each position, we have 2 options. 2 cube. Okay, so this is the sample space. If we toss a coin 3 times. Even we take F as power set of omega. Actually, whenever we have this as countable, whenever we have omega is countable, we usually take F as power set of omega. That means all the subsets as the sigma algebra. And we say this is a discrete probability space. If this is countable, we take F as probability of power set of omega, and we define P in certain way. I'll come to this later. Anyway, so this one we have omega as tossing a coin 3 times. So similar way we can show x number of heads is a random variable on this omega. Same thing. X h h h will be 3, x h t h and all these things will be 2, this one x will be 3, this one x2, this is x equals to 1, x equals to 1, x equals to 1, right? Write down. X of h is 3, x of h is 2, x of h is 2, x of EH is 2, x of EH is 1, x of HTT equals to 1, and x of TTH is 1 and x of TTT is 0. X is a random variable. We define a random variable. We still, any mistake? X of HH is 3, x of HHT is 2, x of HTH is 2, number of heads, number of each. This is a random variable. So x is a random variable. It is number of heads. We still don't know what is probability measure. We still don't know. We can define a random variable without knowing the probability measure. Now we are defining probability measure. So P of x, not P of x, it should be like probability of head in a coin toss. Probability of head in a coin toss is P. Then probability of tails in a coin toss is Q, and P plus Q equals to 1. This is in general. If the coin is if the coin is perfect and no cheating, then P equals to half, Q equals to half. But in general, the coin can be the one side of a coin can be deformed, so it may be not half. Maybe more probability to get a head than get a tail. So we write this as P and Q. If it is perfect coin, we have P equals to half, Q equals to half. Okay. So since we have P and Q, we have this probability P. We can find out probability x equals to 3. Probability x equals to 3, or this is same as probability of, you still remember I write this is omega is sample space and the small omega, any point from omega is sample point. Any point from sample space is sample point. So probability omega belonging to omega such that x omega equals to 3. This is the full sentence. Probability of omega belonging to omega such that x omega equals to 3. In short, we write probability x equals to 3. We can understand probability x equals to 3 means this one. But the actual sentence is probability of omega belonging to capital omega such that x omega equals to 3. So this will be probability of, right, for which omega x omega is 3? For this one. This is the capital omega, sample space. All these are these are sample points, and we denote by small omega. Anything belonging to sample space is denoted by small omega, sample points. So this is the omega for which x omega is 3. This is how much? 1 by p q. Because we have defined probability of head in a toss is p. Here we got 3 heads. So it will be 1 by p, 1 by p, 1 by p. 1 by pq. Similarly, probability x equals to 1. So probability of omega belongs to omega such that x omega equals to 1. This means probability of what are the points? What are the points? X omega 1 for which one? Huh? Which one? From this which one? This one. For which x is 1. So THT, HTT, TPH. We need probability of x equals to 1. We need probability of x equals to 1. X equals to 1 means all those small omega for which x omega equals to 1. Right? This one I should have told this thing first. Anyway, this will be probability of THT is probability of THT. One head is 1p, one tail is 1q. So here we got 2 tail, 1 h. So sorry, p q square. And I will define discrete probability space first. Otherwise, this is plus probability of all the points will be probability of THT plus probability of HTT plus probability of TTH. So this plus PQ square plus PQ square, 3PQ square. Okay, so we need probability after we define random variable. Random variable just needed the sample space and the sigma algebra. If now I define this one first, otherwise discrete probability space. Why this is easy? Because number one is omega is countable or finite, and we take the sigma algebra as power set of omega. So no need of checking whether random variable is measurable function or not. Everything will be in this. So if you are given a discrete probability space, we don't have to check whether the random variable is measurable function or not. And so omega is countable. We can write countable means we can write omega 1, omega 2, first point, second point, third point, and so on. So suppose the capital omega is this thing. We write this probability of x equals to omega I as pi. Probability of x equals to omega I is pi. And then probability of what to write? X belongs to A is summation this. Now check with this example. We are given the omega. This is omega 1, omega 2 and so on. And the f is power set of omega. We have defined probability like this. How did we define? This is the definition of probability measure function. It is probability of this point. H is PQ. You see, probability x equals to omega is PI. So this is the PI. Probability of T is QQ. Suppose this is P1, P2 and so on. Discrete probability space means we have a countable set. We have a countable set or finite or countable set. So we can write down all the sample points. This is only 3 times coin toss. If we toss the coin infinite times, this will be infinite set. We cannot continue like this. Because that is countable, we can write down the sample space as some points. So we can write down probability of x equals to this as PI. Just denote this by PI. So we define, if we say probability of head in a coin toss is P, then probability of x equals to, this is omega 1, omega 2, omega 3, right? This is the omega 1, omega 2, omega 3 and omega 8. We have defined probability x equals to omega I as Pi. So probability x equals to omega 1 is P1. So probability of, should write probability of x equals to H. This is omega 1, right? This is omega 1. So probability x equals to omega 1. This one is P1. We say this one is P1. Then probability of omega 2 is P2. That means probability of x equals to omega 2, HHT. This is P2. And what is the value by this definition? This is P square Q. So P2 is here P square Q. And then if A is an event, means if we say the event as number, okay, A can be is all those toss when first toss gives a head. An event can be first toss gives a head, means probability x belongs to A equals to, in full sentence, all those omega from here such that x omega belongs to A. That means all those omega for which first number is H. The event, this is event is first toss gives a head. What will be the probability of x of a random variable such that its first toss gives a head? That means probability of omega such that x omega belongs to A, such that the first number is head. So this is probability of HHH only 3. Okay, so this one probability of HHH is PQ. This one is p square q. This one is p square q. So this is the thing. H? O. Okay, so HTT. So plus PQ square. So again, discrete probability space is a countable sample space, and if is partial of omega. Since countable